Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. In this hour, we're going to throw the lines open because it's open mic on Science Fantastic. And ask that question, make that comment, and perhaps your thoughts will be heard across the country on national radio. And just remember that some people say, well, gee, maybe I'm not smart enough, or maybe my questions are too dumb. Just remember, if you have a question, chances are thousands of other people have exactly that same so-called dumb question. And sometimes the dumb questions are the most profound questions of all. Science starts with that dumb question. That's why we have so many advances in science, precisely because people ask those dumb questions. Okay, well, let's just jump right into the first listener phone call.
Hello, my name is Krish from Cupertino, California. My question relates to reactionless propulsion. And when I say reactionless, I do not mean any false impressions like electromagnetic levitation, centrifugal force, or anti-gravity, etc. Today, if I tell anyone about a concept for reactionless propulsion, everyone suggests me to first develop a theory which would be hundreds of times harder than just conducting the experiment and finding it out. On the other hand, whenever we enabled frictionless motion, I mean invention of wheel, the actual theory was followed thousands of years later. Why is this contrast? Has the theoretical advancement become a barrier to non-incremental experimentation? Especially because current theories, which by the way are great for incremental stuff, but we do not know whether they will even turn out to be consistent with the reactionless propulsion or not. Your thoughts, please. Thank you.
Okay, well, first of all, I'll give you a reaction to your question about a reactionless propulsion, and then I'll give you some advice about what to do with your theory. First of all, we have Newton's 3 laws of motion, and reactionless propulsion would violate the third law. Let's go through the 3 laws very simply. The first law of motion, you know if you go ice skating, and that is an object in motion, stays in motion unless acted on by an outside force. So if I have an ice puck, for example, and I throw it on an ice rink, it seems to go on forever. In fact, it will go on forever if it wasn't for friction, which is an outside force. So in outer space, if you are in motion in outer space, in principle, you go forever without stopping. And that's how our space probes can go all the way out to Pluto and beyond. They coast. They coast once they're in outer space. They don't need rocket fuel. They don't need large amounts of gasoline to reach Pluto. No, they simply coast because there's no friction in outer space. The second law of Newton is force is equal to mass times acceleration. That gives us equations by which we can calculate the tensions on a bridge, the tensions in a rocket ship, and the tensions in the Empire State Building. You know, when I was a kid growing up in California, I used to hear about the Empire State Building, and I used to wonder, how can they build the Empire State Building without knowing ahead of time if it's going to fall down? I mean, you can't make a model, right, of the Empire State Building that's realistic. So how do they know it's not going to fall down? Well, the answer is we have Newton's second law of motion, and that allows you to calculate the stresses on every single brick inside the Empire State Building. In fact, now that I teach physics, I actually give students problems like that, calculate the tensions inside a bridge. Next, we have Newton's third law of motion, which deals with reaction. The third law of motion is known to every child who's ever blown up a balloon. When you release the air on the balloon goes shooting out in the opposite direction. So air goes in one way, out the nozzle, and the balloon goes the other direction. That is action-reaction. Now, what this listener proposes is a reactionless propulsion. That is, propulsion like a rocket ship without the rocket. That is, without the exhaust. Now, that'd be great. For example, if I have a reactionless propulsion for a gun, I can shoot the gun and not feel the recoil. But if you ever fired a gun, and I fired many guns because I was in the United States military for about 2 years, when I fired machine guns when I was in the military, I realized that there was a back reaction on my shoulder. And therefore, you have to sort of grit your teeth, knowing that when you fire a machine gun, you're going to get that rapid fire reaction on your shoulder, which could actually hurt. Now, same thing with rockets. If you have a reactionless propulsion system, it means you can have the rocket without the fuel. In other words, it would take off pretty much all by itself because you need the fuel for action, and then the reaction is motion in the forward direction. Well, so far we see no violation of Newton's third law of motion. We have skyscrapers, rockets, bulldozers, buildings. At no point do we see a violation of Newton's third law of motion. That's why some people think that the search for a reactionless propulsion is futile. Now, let's say you have a theory, then what are you going to do about it? Some people are hesitant to publish that theory because then your rivals will scoop you and steal your invention. Well, what you ought to do is several things. One, get a patent. In fact, you may want to consult with a patent attorney to get that patent. However, many patent officers require a model that works. Well, let me take a short commercial break, and after that break, I'll give you a word of advice if you have a great invention and you want to make sure that no one steals your idea. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a question about reactionless propulsion. Many people have tried to create that because then you could basically have motion without the rocket fuel. Think about that. Rockets without rocket fuel. However, Newton's has the last word. For every action, there's a reaction. And we know that because we've tested it on rockets, airplanes, we've tested it on bulldozers, skyscrapers. Every time there's an action, there is a reaction. And that's codified in something called the conservation of momentum. So, sorry about that. If you are an inventor, I would suggest you try to invent something else other than something that violates Newton's third law of motion. However, if you do have a theory, what are the steps that you should pursue? Well, first of all, you may want to take a patent out on it. However, I warn you that if you have a patent for a perpetual motion machine, usually they ask for a demonstration model. So many people over the centuries have claimed to have created a perpetual motion machine. Energy from nothing. In fact, in antiquity, going back thousands of years, enterprising inventors would go to the king and claim that they can get energy for free. Usually it was some kind of spinning wheel of some sort. And of course, because of friction, you basically lose energy and have to add energy from the outside. But anyway, over thousands of years, people have tried to get inventions sponsored by the king, in which case they could become millionaires in the process. However, after centuries of analyzing all these perpetual motion machines, we physicists have come to the conclusion that there's something called the conservation of energy, which in turn is a byproduct of Newton's laws of motion. So in other words, the patent office will ask you for a demonstration model. Don't just think you can create something in the laboratory and become an instant millionaire. However, I do suggest that if you do have an idea, patent it. Talk to a patent attorney Or if you simply want recognition for your idea and not necessarily to commercialize it, publish it in a magazine. There's several magazines you can submit it to. There's Physical Review, which is the magazine of my organization, the American Physical Society. It is the premier American physics magazine, Physical Review. There's also a European magazine, Nuclear Physics, for example, published by Elsevier Publishers in Europe. They are one of the leading publishers of nuclear information papers in the nuclear field. So if you have an idea and you don't want to patent it, but you want recognition for that theory, then you may want to send it to these magazines, and then you will get a referee. Sometimes more than one referee. In fact, I referee other people's papers all the time. Magazines send me articles to referee for their magazine. In fact, just last week, I got a article that a magazine wanted me to referee an article about astronautics of interstellar space travel. So those are the paths you can take if you have an idea and you don't want someone else to steal that idea. By the way, don't take it personally. Sometimes the referees can be brutal, but they'll be honest with you. The referee will tell you honestly why they think your idea is great or why it's a bunch of nonsense. Okay, let's move on now to the next listener phone call.
This is Armand again from Queens. Listening on YouTube. So you know how you lucid dream? I was wondering if there's one day you think there'll be technology to make you able to control your dreams while you're sleeping, so you can actually function on in a virtual world while you're sleeping, while you're getting like a good night's deep sleep. All right, thank you very much for that, and I love your show, and have a great day. Bye.
Okay, good. Well, just a few years ago, if you were to ask a question to a scientist about lucid dreaming, they would have considered you to be a crackpot. Well, not anymore. Lucid dreaming, that is the idea that you can control the progress of a dream, is actually correct. There are lucid dreamers who've been subjected to an MRI scan. When they fall asleep inside an MRI machine that analyzes blood flow. It turns out that when you dream, the blood to the prefrontal cortex, which is the thinking part of your brain behind your forehead, shuts down. That's why your dreams become fantastic. They violate all the laws of logic, not just the laws of physics. They violate the laws of logic because the front part of your brain is drained of blood when you dream. And then MRI scans show that the center part of your brain, that is the amygdala, lights up like a Christmas tree. And that's the seat of nightmares, the seat of emotions, the amygdala. And that's one reason why many of your dreams are nightmarish. So it turns out that people who are lucid dreamers have an active prefrontal cortex while the amygdala lights up. Both areas of the brain light up. So in other words, it's true. Not only that, but when you dream, you are paralyzed. So how do you talk to someone who's a lucid dreamer? You give them a piece of electrode in their hand, and you ask them to squeeze it. Even though they are paralyzed when they dream, they have the ability to squeeze gently an electrode in their hand. And that's how you can communicate. That's how you can actually talk to someone who's dreaming and communicate with them. And they can communicate with you by squeezing this electrode. This has actually been done now at the Max Planck Institute in Leipzig, Germany. They put a German who claimed to be a lucid dreamer inside the machine, and bingo, the prefrontal cortex was fully lit up even as he was in REM dreaming state. So in other words, lucid dreaming is scientifically possible. Then the next question is, how do you become a lucid dreamer? It turns out that Buddhist texts going back centuries have given people lessons as to how to become a lucid dreamer so that you can control the direction of your dreams. You can Google it. Some of these things are common sense. One is that just before you go to bed, you have a notebook. You see, when you wake up, right after a dream, you forget the dream within a matter of seconds. Within a matter of seconds, the memory of that dream simply disappears forever. So have a notebook. Write down the dream. Get in the habit of writing down the dream as soon as you have it, as soon as you wake up. Second, prime yourself. That is, before going to bed, say to yourself, I'm going to be a lucid dreamer tonight. I'm going to be awake. I'm going to control the direction of my dream. So get in that frame of mind that you are going to control the direction of your dream when you dream that night. Now, of course, we can't guarantee that you're going to become a lucid dreamer. However, the lessons are centuries old as to how to control the direction of your dreams. This is not science fiction anymore. We actually can do it now in the laboratory. Okay, let's move on to the next listener phone call.
Hi, Dr. Kaku. My name is Tim. I'm calling you from Dallas, Texas. My question regards dark matter. Is dark matter just matter that we cannot observe via visible light, or is it just something nebulous and unknown in the universe? I know that it makes up so much of the universe, and we don't know very much about it. So your thoughts on the matter would be very well appreciated. Thank you very much.
Okay, good question. Well, every high school textbook has to be rewritten. All the high school textbooks say that the universe is basically made out of atoms, but that's not true anymore. We know that there's something called dark matter, which outweighs ordinary matter by a factor of maybe up to 10. Now, how do we know that? First of all, the galaxy, the Milky Way galaxy, well, unfortunately, I have to take a short commercial break, but after the break, we're going to talk about dark matter. How do we know it exists? How do we have maps of dark matter? And what is it anyway? And why is it important? Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open because this is Open Mic on Science Fantastic. You know, I was on a book tour years ago, and a guy comes up to me once after my talk, and he says, you have to answer my question. You just have to answer my question. And I said to him, well, that's very nice. I'll answer your question, but why do I have to answer your question? And then he said, because if you don't answer my question, I may have to wait another 10, 20 years before another theoretical physicist comes by and can answer this question. And I was taken aback. And I thought to myself, and I said, he's right. You know, there are very few theoretical physicists in this world. And how many of them are going to be passing through this small town, signing copies of his book, answering detailed questions about string theory, about Einstein's theory of general relativity, about the unified field theory? So anyway, the point here is, if you want to ask a question, give us a call at 612-564-8135. You get a recording, leave your name, the city you're calling from, and then ask that question. Make that comment, and perhaps you can get on national radio. Okay, let's move on now to the next listener. Oh, by the way, I forgot. I have to answer the question about dark matter before we move on. Dark matter was first found by astronomers decades ago, but it was dismissed because it was too preposterous. For example, the Milky Way galaxy spins. It looks like a pinwheel, in fact, but it spins 10 times too fast. By rights, it should fly apart. In which case, the Earth should have been flung into outer space billions of years ago. But the Milky Way galaxy is quite stable, and we see these galaxies everywhere in the universe that are very stable, but all of them are spinning about 10 times too fast. Either this means that Newton was wrong, and we are very reluctant to give on Newton's laws of gravity. Either Newton was wrong, or there's a new form of matter in a halo surrounding the galaxy, keeping the galaxy intact, preventing it from flying apart. That's dark matter. Now we have maps of dark matter. Dark matter is invisible because when you photograph these galaxies, we don't see a halo around these galaxies at all. We just see a pinwheel. But they're stable, and they spin 10 times too fast, and we now have maps of dark matter. When light goes through glass, it bends light. So how do you know that there's glass inside your glasses? Well, glass is invisible. So how do you know that there's glass inside your glasses? Because light bends when it goes through your glass, and that's why you have eyeglasses. Same thing with dark matter. When light goes through this invisible matter, it bends. Then, using a computer, we can calculate how much dark matter there is by calculating how much bending of light there is. And you can Google it. You can actually see maps of dark matter reconstructed using computers looking at the bending of starlight. Well, let's take a short break, and afterwards we'll talk about what is dark matter anyway, and why should you care. Once again, this is Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a question about something that is requiring us to rewrite all the high school textbooks, and that is the presence of dark matter. What is it, and why should we care? Well, first of all, as we mentioned before, we have maps of dark matter which surrounds the Milky Way galaxy, holding the galaxy together so that it doesn't fly apart. And the next question is, what is dark matter made of? Well, the short answer is we don't know. There's a Nobel Prize waiting for that person who could finally tell us what dark matter is. However, there are many theories. The leading theory is that it's a new particle. We call it the photino, a particle that is the companion to the photon, which is a particle of light. The photino is invisible. It is predicted by a theory called string theory, which is what I do for a living. And it is plentiful and invisible, but has mass. These are exactly the characteristics you want dark matter to have. You want it to have gravity, so it holds the galaxy together. You want it to be invisible, because we don't see anything with our telescopes when we look for that halo surrounding the galaxy. And this particle is predicted by string theory. String theory has not been proven, but it simply says that all matter consists of vibrations. Vibrations of a tiny rubber band. When the rubber band vibrates in different frequencies, you get different subatomic particles. Now, why don't scientists all uniformly agree with string theory? It's a controversial theory. Among other things, it states that the universe is not three-dimensional at all. We think that everything is three-dimensional. You can describe everything by its length, width, and height. However, string theory says that there are 11 dimensions, that our universe is a bubble floating in a much larger hyperspace universe. That's controversial. That's why some people don't like string theory at all, because it forces you to confront a many worlds. The idea that our universe is not just one bubble that's expanding, an idea given to us by Einstein, but there could be many bubbles out there, a multiverse of universes. Now, there is another way to explain dark matter, and that is, if there are these other universes, then matter can exist, stars can exist in these other universes. If these two universes are close together, we would feel the effect of gravity from this other universe, but it would be invisible, because light can only move in our bubble. Therefore, if you hover in hyperspace, you are invisible, but you exert gravity. But that's exactly what dark matter is. It's invisible, but exerts gravity. Now, that is a pretty wild theory, a theory that we are very close to a parallel universe where there are parallel galaxies out there, and that's what causes the halo. Well, personally, I believe in the first theory, that is, for the photino, that is, the particle of the photon, is the origin of dark matter. And why should we care? Well, first of all, we are here today because of dark matter. If it wasn't for dark matter, the galaxy would have been split apart, would have been flung apart billions of years ago. And if it does turn out that dark matter is consisted of these higher resonances of the string, it'll prove one of the greatest theories of all time. That string theory is, in fact, the theory of everything. The theory that explains the entire universe. The fabled unified field theory, the theory of everything. But that's another story. Okay, let's move on now to the next listener phone call.
Hello, sir. This is Bear, spelled B-A-I-R. Bear Cloth. I found your question on Twitter, and I'm from Medford, Massachusetts. And my science question is, in this universe, is a black hole the other side of the Big Bang in a different universe? Thanks.
Well, at first your idea sounds ridiculous and preposterous, but actually there are physicists, colleagues of mine, who actually published papers in this idea. And this idea is very simple, and that is, if we have black holes, why can't we have white holes? In fact, Stephen Hawking wrote papers on this, the fact that somewhere in the universe there should be the opposite of a black hole, which is a white hole. A white hole, instead of absorbing matter, actually excretes matter, shoots matter out. And then the question is a white hole on the other side of a black hole? Well, we'll talk about that after the break. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a question about white holes. So let me explain. First of all, the laws of physics can run forward or backwards in time. For example, if I get a motion picture and I reverse the direction of time, then, well, bizarre things happen. Food comes out of your mouth and reforms to give you breakfast right in front of you. Dead people come out of graves and reassemble to become living people. So if you ran the videotape backwards, it would be very strange, but possible. Unlikely, highly unlikely that food will come out of your mouth and reform to create the fried egg that you had this morning, but possible. So if you have a black hole that absorbs matter like a vacuum cleaner, then a white hole should also be possible. Unlikely, but possible. But we've looked for white holes and we have not found any at all. But white holes are actually rather convenient, because if everything falls into a black hole, then maybe it spews out the other end as a white hole in another universe. Now, this idea was actually made possible by Einstein himself. In 1935, he asked himself a simple question. If you fall into a black hole, does all matter basically die at that point? What happens to the matter? Maybe it funnels out into another universe. So think of a black hole as being a funnel. A funnel where everything comes in, nothing comes out. But on the other end of the funnel, there's a reverse funnel that's upside down and is attached to the original funnel. So you have two funnels. One funnel, which is the black hole, which absorbs everything, and the other funnel shoots out matter, and that's a white hole. And then several of my colleagues have said, maybe that's the Big Bang. Maybe the Big Bang is really connected to a parent universe. Now, as bizarre as this sounds, this is compatible with an idea called inflation. And inflation, in turn, is the leading theory of the Big Bang. It turns out that Alan Guth at MIT proposed the idea of inflation several decades ago. It fits the data. He may eventually win the Nobel Prize for this theory called inflation, which says that our universe can peel off baby universes. So think of a soap bubble and the soap bubble can peel off baby soap bubbles, and you have this continual peeling off of baby universes. In other words, Big Bangs are happening all the time. Every time you have a peeling off of a baby universe, a black hole becomes a white hole. As preposterous as this sounds, it is compatible with all the data. When you look at the data from our Big Bang, it is compatible with the idea that these Big Bangs happen all the time. Now, does that prove it? No. It only shows that our particular universe seems to have originated from a peeling process from a parent universe. But it is not proof. Proof, we may have to go to another satellite called LISA, Laser Interferometry Space Antenna, which is going to be a gravity wave detector in outer space, which may give us baby pictures of the instant of creation. The instant of creation, the exact microsecond when the baby universe emerged out of the womb, and the hope is we'll detect evidence of an umbilical cord that connects our baby universe to a parent universe. Sounds crazy? Yeah, but hey, this is what we do for a living. We physicists look at the data, and no matter where the data takes us, that's where we go. And so far, our data takes us in the direction of inflation, which in turn makes possible a multiverse of universes. Okay, let's move on now to the next listener phone call.
Hi, my name is Fred Kushner. I'm in Colorado. I'm not currently listening to, but I do listen to our Colorado Public Broadcasting station. And my question is, if the maximum speed limit for any object or electromagnetic radiation in space-time is the speed of light, why is it that space-time itself can expand faster than the speed of light? That would be wonderful if we could answer that question for me. I'm confused.
Okay, well, Einstein's statement that nothing can go faster than the speed of light is slightly incorrect. A more precise statement would be nothing material can go faster than the speed of light. You see, nothing can go faster than the speed of light. I repeat, nothingness can go faster than the speed of light. In other words, nothing can stretch faster than the speed of light. Now, the Big Bang was when we had this explosion of a tiny area which stretched to give us the universe of today. And that stretching process was not material. It was just emptiness. Empty space can expand faster than the speed of light. But material objects cannot go faster than the speed of light. So, for example, here's an example from my youth. When I was a kid, I used to take a flashlight, and I would sweep across the night sky with the flashlight. The flashlight went from one end of the universe to the other end of the universe, thousands and thousands of light years in the other direction. And I said to myself, now wait a minute. I just violated Einstein's theory of relativity, because the image that sweeps across the sky is going faster than the speed of light. Well, I'm a physicist now, and now I realize that, yes, the image went faster than the speed of light, but material objects, that is photons, particles of light, each particle of light did not go faster than the speed of light. Here's another example. Let's say I have a bomber that drops a whole bunch of bombs in a string, and I'm on the ground, and I watch all these bombs hit the ground. Each bomb is moving very slowly as it slowly falls toward the earth. But when I look at the image point of where the bombs hit the ground and then rapidly go bum, 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 bum in a line, I realize that that can go faster than the velocity of the bomb itself. So in other words, the image can go faster than the speed of light because it's not material, but not the bomb itself. Okay, well, unfortunately, we have run out of time. Once again, this is Science Fantastic with Professor Michio Kaku.